Might be a bit loud. It's fine.
Yeah, I'll meet you on the dance floor. Can you meet me on the dance floor? Yeah, I see you on the dance floor. Can you meet me on the dance floor? 'Cause I wanna
Anyway, how y'all doing? Spotify decided it wanted to throw a fit and not work, so I said, okay, we'll let you throw your little fit, and we'll worry about it next time, I guess. It's also using an absurd amount of CPU, and I don't know exactly where that's going, but I get the feeling it's Spotify, so if I close those two... No, not really. Yeah, I don't know what's going on there. That's too bad. Anyway. Hey, Famished. Alright. We'll stick it somewhere around there. That should, in theory, work. So I hope everybody's doing alright. We are going to be talking about... What are we on now? Night 6? Night 7. Cracking the GRE math test. Second edition from 2002. So, we're going to be dealing with more of the trigonometry that we were talking about last time around. Trying to get trig better understood. Again, I'm going more for a, like, how would you actually teach this approach, not a how do you hack the exam to give yourself better, give yourself better test-taking strategies. It's not really what I'm about. I know that there are also various shortcuts that you can take, but the shortcuts really only help when you actually know what you're doing, at least most of the time. One more course to finish in online school. Nice, nice.
At Sky Vegas, get 50 seriously free spins when you join, and 200 more when you deposit and spend £10. No wagering required. What you win is what you keep. Sky Vegas. Play. It's why we're here.
Our daughter definitely pulled a, very much us. And was like, oh, yeah, I got my exam results back. I did alright. And like, okay, what does that mean? Because alright around here typically means like, you got like a 50 and the teacher's gonna scale everything. Throw everything onto a curve and, it'll all work out in the end, but like, half the class failed by American standards. So, like, what does that mean exactly? And she was like, yeah, I mean, I did alright. I got like a 98 in both my math exams. I'm like, I don't think you understand what that word means. And yes, out of 100. And she was like, I got a 91 in my religious studies, which I wasn't expecting. Like, respectable. So it's like all A's across the board, and we're like, You are doing outstanding, and you should know this. At the same time, I don't want to, like, you know, inflate your ego too much. Trying to finish before before 2026. You only have one class left, right? So, or do you mean just one more online class, but then multiple others that you have to physically go to? No, that makes sense. Oh, right. I closed that window. There we go. Boop. And we're back. Okay. So last time we were discussing that we wanted to make sure that we were, that's definitely going to get DMCA'd, you punks. You could not play Elvis. Nope. Oh, I have that emote, actually. There we go. No playing Elvis. Okay. So you got 3 more semesters. Nice. So last time we were discussing that there are kind of 2 ways to look at all of the individual trigonometric function values. So the first one was looking at our sine, cosine, and tangent, and secant immediately off the bat. So up here we're looking at this. Our horizontal value, x, if it's on a unit circle, where r is 1, then we end up with the cosine function value represented by the horizontal distance to get to whatever point we're on going around the circle. Still feel like that might be a little loud, but I can't tell. How y'all doing? I might just need to turn myself down, so that's fine. Or turn my headphones down. The vertical value, or y distance, from whatever point we're at down to the x-axis is going to be represented by our sine length, again, on the unit circle. If we are not on the unit circle, so r is anything but 1, all we have to do is just scale it up and say, oh look, it's bigger. And so when we say it's going to be bigger than 1, or smaller than 1, then our sine value takes on what you all probably remember as the opposite over hypotenuse, y over r in this case. And we listed all these somewhere. Yeah, here we've got our y over r is sine of theta, x over r is cosine of theta, and tangent then is the ratio between them. The length of the tangent line is the tangent on the edge of the circle, which then goes up to wherever our secant meets up with it. And then the secant length is going to be the length that goes out to the tangent line. Right, our secant line that goes through the origin, through the circle, and then touches the tangent line. And then we said we want to talk about the co-secant and co-tangent, and also then the cosine ends up being part of this as well. What we look at here is if we were to draw...
You might expect a delicious sounding description here, but do we really need it?
Seriously, you cannot play these songs. Punks.
Does your home have an RTS meter? It's a switch box with your electricity meter.
Okay, so here we have the distance that goes from
RTS meters is being switched off, and some homes could lose heating and
somewhere on the y-axis out to our point x comma y. And that ends up being the same as our x value, because again, this was down here, and then this is our y value, because again, it's the exact same stuff. It's just on the other side of this rectangle that we've now created. And the important part is that the angle here, pi over 2 minus theta, or the complement of the original theta, now has its sine value as x divided by r, right? Opposite over hypotenuse. So the opposite side is x, the hypotenuse is r still. Alright, that'll be a little better. Okay, so we have x over r, which is now going to be our opposite over hypotenuse of the complementary angle, pi over 2 minus theta. Yeah, pi over 2 minus theta. That being the complementary angle, x over r is considered the complementary sine, hence the name cosine. And then we do the same, right? We talk about the secant line that goes through the circle, through our point x comma y, and then connects with the tangent that is now on the top of the circle. This is now going to be the complementary tangent, or the cotangent, and this is going to be the complementary secant, or the cosecant. Okay. And in each of these cases, we end up with a Pythagorean identity, which is going to be based on cosine squared theta plus sine squared theta equals 1, which is our x squared plus y squared equals r squared. We could do that whether we have r equals 1 or r equals literally any other number, because our sines and our cosines, remember, are x over r and y over r respectively. Or maybe reverse, respectively, as I have written them. Then that also creates these larger triangles here, which are going to be 1 and the tangent length of theta, and then the secant length of theta. So now we get this identity as well. 1 squared plus tangent squared theta equals secant squared theta. And then similarly for the complementary triangle here, we have our 1 is the radius here squared plus cotangent squared here of theta is equal to cosecant squared of theta here. So now we have 3 different Pythagorean identities, which are represented by these triangles. Alternatively, we can do one diagram that has all 6 of these angles. Everybody's favorite. Woo! What we've done is we've taken a radius that goes out to the point xy. Doesn't matter where it is, right? Anywhere you want to put it. These are going to have the same overall values. So, our horizontal value is represented by, again, the cosine of theta, no matter what quadrant we're in. The vertical value is given by the sine of theta when r is 1. The tangent length is going from, and this is kind of key here, it's going from our point xy out to the x-axis. Chad in Coke. On Coke? Oh, I hope not. I wonder if this is fixed yet. Oh. Somebody needs to poke the Enigma server. With a stick, preferably. The distance from the point xy at right angles to our radius is our tangent to the circle at that point, and the tangent length going from xy down to the x-axis, regardless of which direction it's going, right, down to the x-axis, is going to be the tangent of theta. Going the other direction now, we have the cotangent of theta, which goes from our point xy to the y-axis, whichever way it goes, again, up or down. Depending on where you are on the circle, you're going to get different points. Okay, then right, going outward, we have the secant length is going from our origin point along the x-axis until it meets the tangent, and our cosecant goes along the y-axis until it meets the cotangent. So now we have all 6 of our trigonometric functions in one diagram. And helpful, believe it or not, it is helpful, where these trigonometric functions connect to our x and y axes, particularly our tangent, secant, cosecant, cotangent, that will tell you precisely whether you have a positive or a negative value of that particular function. There's a few different ways to think about it. So what we've got now is our tangent of theta is dealing with the x values divided by the y values. So here in the positive x direction and in the positive y direction, right, x over y is going to be positive. Okay, over in the second quadrant, tangent of theta, we have our y value, which is positive because we're up still, and then we have our x value, which is negative because we're off to the left. Interestingly, right, that makes it negative over here. Okay. Down in the third quadrant, we have, I probably should have mentioned that. This is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. It's kind of important. But this is why we label them 1, 2, 3, 4 in that order. We are going around the unit circle and we're counting them off in order that we meet them as we open the angle. Right, so our y values in the third quadrant are negative because it's down, and our x values are negative because it's left. Well, that means that we have a negative divided by a negative, so that makes it positive. And over in the fourth quadrant, we've got the tangent of theta, which is going to be, again here, y values are negative because we're down, and x values are positive because we're right. So now we have a mixed case. That means that here we're going to get this to be the tangent is less than 0. Now, interestingly enough, right, this is going to get us, if you look at it, right, we're going to have a radius that, if we're in quadrant 2, is going this way, and in quadrant 4 is going this way. I'm just putting them opposite each other because it's easier to see, but the fact that it's, you know, and the fact that we have to go through the origin. These angles don't have to be, like, opposite each other. So what we've got now is a second quadrant going up this way, and a fourth quadrant going down this way. You notice here that this makes a straight line. And what's a major feature of straight lines? Well, we could think about it as, especially ones that go through the origin here, we're not dealing with y-intercepts. So we're dealing with slope. And if you look at it, our slope is less than 0 in both of these cases. And if we go the other way,
watching me on a phone is like watching a sunrise through a straw. Some things belong on the big screen.
slope is greater than 1 on this side, and slope is greater than 1 down here as well, or greater than 0. Greater than 0 down here as well. So here we have identical matching, or at least sign cases, right? All of the individual signs, positive, negative, between tangents and slopes. Well, let's see if we can push this any further. So we go in here and we say that we just said that the tangent of theta was going to be given as y over x when we're dealing with the point x comma y. And it also goes through the origin. So what if we subtract those respective points, or coordinates, x and y, 0 and 0, from x comma y prior to it here? Well, this is the exact same thing as the slope. Right? Slope of the line through 0, 0, and xy. So we've just verified it here that, yeah, in fact, our tangent of theta, the value that we get from the tangent of theta, is equal to our slope. Not just like influenced by it, not just they happen to have the same sign, numerical sign to them. No, they have the same numerical value as well. 100% identical value. So that does mean that we can actually say that whatever the slope of our radius, right, the line that goes from the origin out to xy is our radius. The terminal side of the angle. Right? It is the terminal side of the angle theta. And whatever the slope of that line is, whatever the slope of the terminal side of the angle of theta is, that is our tangent of theta value. I don't know. That's pretty cool. Makes it a lot easier to work with. And we already just dealt with the fact that the sine value and the cosine value, again on a unit circle, are respectively the y value and the x value to the coordinate point. So that's pretty cool. That says that 3 of these things are directly linked to super easy stuff that we can just, you know, get numbers for. Right, so again, oh, and you know what? It doesn't even matter. Tangent, it doesn't matter if it's the unit circle or not, because the slope is going to be the same anywhere along this line. Right? As long as the line is the same, it doesn't matter what size circle you have. Now, the other stuff does depend on r. So our sine, our cosine, our secant, and our cosecant all depend on the r value. But tangent and cotangent don't. Right, so cotangent of theta is going to be equal to x over y. So this is the multiplicative inverse of the slope. Right, our cosine of theta is equal to x over r, which equals x if r is equal to 1. And similarly, sine of theta equals y over r, which is equal to just y when r is equal to 1. I don't need that space or whatever. Slightly awkward. That's fine. Right, so the secant of theta is going to be r over x, or, again, just 1 over x when r is equal to 1. Alright, what's this? Well, it's the multiplicative inverse of the x value. You can actually do this geometrically. I'm not actually sure how to do it, but Simon Padilla does it on Numberphile. He actually has a like compass instrument that will draw out it'll draw out a standard radius, like wherever you want to put it, and then when you dial in like an inner compass, it'll throw out the multiplicative inverse from it. I think it only goes to like half, so that you can only go out to twice as far as the original circle radius, but something like that. You might have a better one that goes like 10 times, but you know, that'd be crazy.
Now it's even easier to sell for free on eBay. I was thinking, maybe I should sell that juicer we've used a grand total of once. Or the shirt I've been saying I'll wear for the last 2 years, but never have. Or that tiger cushion the dog barks at every time he's in the lounge. Oh, is that it again? No, Bertie!
With new AI listing features and simple delivery, it's now even easier to sell for free on eBay. Download the app now. eBay. Things people love. T's and C's apply. Excludes vehicles.
All right, and our cosecant of theta is going to be r over y, which is then going to be 1 over y on r equals 1, where that's going to just be the multiplicative inverse of the y coordinate. So, same deal. It's all the same. Again, r equals 1. So that works out rather quite nicely. And again, where each of these things are positive or negative is just going to depend on where your x and y coordinates are. So in terms of right, your secant of theta is going to be greater than 0 on this side, and secant of theta is going to be less than 0 on this side, because the secant is based on the x values, which are based on the horizontal values. So, since they're based on x, right, you got positives this way, you got negatives that way. Yeah, that's right. Sorry, I'm backwards to you, so... Right, we've also got the cosecant of theta is going to be greater than 0 going up, and cosecant of theta is going to be less than 0 going down. Why? Because they're based on the y values. And that also works for the sine of theta in both of those cases. This secant of theta also works for cosine of theta for both of these cases. Right? It's all the same stuff. We're just basing everything on its x and y coordinate values. So place any particular point that you want on the unit circle, or make it any non-unit circle. So let's pick a point that's out here, negative 12, 13. Now I'm cheating here because that's a nice Pythagorean triple, but nonetheless, right? Let's pick this as the first one. Right? Find all 6 trigonometric function values at this point. Right, what we've got here is we have an x value that is negative 12. We have a y value which is 13. Oh, that's not a nice Pythagorean. Never mind. 5, 12, 13 would have been nice. Okay. Negative 12 for x, positive 12 for y. Find all 6 trigonometric function values. Okay, so what we need then is what's r, because now we need to know for all 6 trigonometric functions, right, what is our x, y, and r. So r is equal to, r squared is equal to x squared plus y squared. R squared is equal to, this is negative 12 parentheses squared plus 13 squared, which is 144 plus 169, which is 313, which is r squared. Therefore, r is equal to the square root of 313. It's not divisible by 3, any even number, or anything obvious. So what I usually do for this, if I think that there is a nice number that we can divide by to take out any particular values when we're simplifying square roots, oftentimes I will plug it into my calculator oops, as the radicand over x. So in this case, 313 over x. And then I go to the table. So second graph. Also make sure your table set is correct. Set it to independent, automatic on both of these. And then this is going to give you a long list of numbers. And you might be thinking, why on earth would I do that? This is because what we can do here is we can say, all right, well, if we divide 313 by 1, we get 313, obviously. Then we can go to all of the, specifically, we can go to all of the nice numbers, which get us factors, or if we're feeling really ambitious, or if you just want to save some time, you can just ask for all of the square numbers. So you could actually set table set for ask on independent, and then just manually input, 1, 4, 9, 16, 25, 36, etc., and keep doing that. And then all you have to do is just look down the list and see if any of those end up getting you a nice division. Now, at the moment, there aren't any. So, these are all going to be nasty decimals. It's not really all that surprising. 313 did not look like a particularly nice number, and as it turns out, 313 appears to be prime. Now, you only have to go as far as the square root of 313. Because after that number, any possible factor pairs will just swap. So if you think about, 64, I guess, right? If we wanted to know 64, and then we could split it down, break it up, we could get 1 and 64, or 2 and 32. Yes, I know that it's not that hard, but still. 4 and 16, 8 and 8. Then the next one down the list on the left is going to be 16, which has a factor pair of 4. So again, after square root of 64, columns flip. And don't do that to yourself, right? Don't bother writing anything more. We don't need these. We already did that factor pair. It's here. So we just look and see, is there any particular factor pair which is going to work up until we hit the square root of 313, which is approximately 18. It's like 17 and a half or something. And there aren't any. They're all nasty decimals until that point. So now we're done. You only have to check like 17 numbers in your calculator. So 313 is the simplest radical that we can get. Asterisk. For this particular example, it's the best we can do. So here, right, 313 is prime. So we don't have any numbers which will divide 313 evenly after 1 and until 313. So what we have now is a square root 313 on the radius, and then we have our 12 and 13 as negative 12, and 13 as our x and y values respectively. Now, this is theta. However, this angle right here is often what we call theta prime. Inside of a standard right triangle, theta prime has all the same properties as theta. So the proper angle theta, which is in the second quadrant, which is bigger than 90 degrees, can't belong to a 90 degree, right triangle. It's not possible. On the other hand, it can drop an altitude and create a right triangle in that little hole there. And that angle over there is theta prime. It is the what do we call that? Reference. There we go. Theta prime is called the reference angle. For theta. F of theta prime is going to be equal to... Yeah, if we get that is okay. So what we're looking at is the cracking the GRE math test. Basically, I am going through and talking about how to learn all of the topics that are in here. So whereas maybe somebody might be like, here's the quick and dirty way to get this answer. I'm going to be looking more at the conceptual understanding of it rather than the quick and dirty way to just get an answer. Because honestly, that's only going to serve you once. And then once you move on to the next question, you may have no idea what's going on. Or if you mean in general, it is conceptual understanding rather than very specific questions. But you can always let me know exactly what you mean. All right. So, whatever trig function you're using for theta prime, it's going to be equal to the absolute value of that same function of just theta. So, the trig function of theta prime will always get you a positive value because theta prime is effectively in quadrant 1. It's between 0 and 90 degrees, and that's it. Whereas theta can be any angle along the entire circle. And the trig functions of those things will get you any particular value. Depends on where it is. Again, depending on which trig function we're using, they've got x's and y's and r's. Any of them could be positive or negative. Well, the x's and y's could be positive or negative in any combination. Okay, and then what we do here is we say all 6 of the trig functions. We've got sine theta, cosine theta, tangent theta. Secant theta, cosecant theta, cotangent theta. If you want to reorder these and put them in whatever order you feel like, or if your teacher reorders them into any particular order, feel free to switch. But the major point is that, again, our sine of theta, cosine, tangent, etc. all have this combination that we were looking at earlier. Sine is y over r, cosine is x over r, tangent is y over x, secant is r over x, cosecant is r over y, and cotangent is x over y. So with the 3 values that we just created inside that unit circle, no, that is not a unit circle, inside of that circle, we end up with a sine value that is going to be y is 13 divided by square root 313. spread them out a bit. Cosine of theta is going to be negative 12 divided by the square root of 313. And tangent, y over x, is going to be 13 over negative 12. R over x, our secant, is going to be a negative root 313 over 12. Our cosecant is going to be r over y, which is the multiplicative inverse of sine. So that's going to be our root 313 over 13. And cotangent is negative 12 over 13. Now, depending on the pickiness of your teacher, you may also get somebody who says that you need to rationalize the denominators. Quite frankly, I don't care, right? It's not my particular quirk that matters. It's going to be whatever your teacher wants. But literally, this does not matter to me. And in fact, this is a perfectly valid answer. And I think that this is actually superior in many ways because this shows me that you understand that this is going to be y over r. And in the real world, most people don't bother rationalizing denominators, especially when you end up with something that looks like 13 square roots of 313 divided by 313. Right? We multiply both top and bottom by the square root of 313 to rationalize the denominator, get it out of the radical. It's just how this one works, right? This is going to be negative 12 square roots of 313 divided by 313. And all the rest of them are already rationalized. But also, if anybody does have any questions, you can just interrupt me from whatever I'm doing, because I'm going to go through conceptual stuff. So, once we do the concept, we do some practice, etc., etc. But if anybody has requests, please feel free. We can pop that into the chat down there. We can throw it into the Elements Discord.
Now it's even easier to sell for I was thinking, maybe I should sell that juicer we've used a grand total of once. Or the shirt I've been saying I'll wear for the last 2 years, but never have. Or that tiger cushion the dog barks at every time he's in the lounge.
Invite.
No, Bertie.
Copy.
AI listing features and simple delivery. It's now even easier to sell for free on
Okay.
eBay. Download the app now. eBay. Things people love. T's and C's apply. Excludes vehicles.
So this is Penn Center's Discord. Penn Center is a department chair in British Columbia, and also does a bunch of Twitch streaming, which includes doing a class, which I should know this. I went to it the other day. Oh, was it complex analysis? Oh, machine learning. There we go. Yep. So Penn Center's been working on machine learning lately. Okay. Okay. So, in terms of some of the stuff that we've been looking at, this would be the kind of thing that I would expect a student to be able to practice and understand. Make sure that you get how to pick literally any angle that is on the unit circle. It doesn't matter if it's nice or not. If it goes through a particular point, then this is how we do it, right? As far as I know. So your dimensions and tensors aren't necessarily spatial dimensions. They often are, but they don't have to be. Okay. No? Okay. Doing okay? No. Are you sure you're still watching? Yes. So if you have some sort of, nice angle, which is going to be something like theta equals, hell, let's just do like 17 pi over 3. You need to be able to put this into a form which makes sense. So first of all, right, where is theta? What is its coterminal angle such that coterminal angle, let's call it phi, such that phi is between 0 and 2 pi. So we just want, like, where is this on the standard unit circle? This is actually probably number 1 that we can figure out. Number 2 is going to be there. Alright, so now I just figured out where it is. 3. What are its trigonometric function values? It is, in fact, a 30, 60, 90, yes. Right. All pi's on 3 that don't simplify end up getting us 60-degree angles on the central angle. So here, right, number 1, if we keep subtracting, so we say, okay, 17 pi over 3 minus, what we want to do is we want to cut out any whole loops that we've gone through. So one full loop is going to be 6 pi on 3, because that's just 2 pi. and then we want to multiply that by as many as we can to get rid of as much fluff, as many of these cycles, complete cycles, as we can. Okay, so then what is that going to be? Well, we can subtract 2 of them off because that's 12 pi on 3. If we try to go to 3 cycles, that's 18 pi on 3, which is going to get us a negative angle. Now, it is easy enough to look at it and be like, okay, well, that's negative 1 pi over 3, right? Phi would end up being negative pi on 3. But then, again, that kind of breaks breaks this idea that we want to have it between 0 and 2 pi. So n equals 2 is going to get us that theta is going to be equal to, or phi is going to be equal to negative pi on 3 plus another, well, no, 17 pi over 3 minus 12 pi over 3 is going to get us 5 pi on 3. Which is in quadrant 4. Alright, we'll be right back after ads. It's going to start here in half a second anyway, so I might as well click the button. So thanks everybody for sticking around. We'll be right back with more of this. We'll finish up the thought here. Again, if anybody has any questions, please feel free to ask in chat or throw it into Penn Center's Discord. We'll be right back. Alright. So to kick off the next hour, we will do our sometimes streamly reading from John Gould's Maine Lingo, A Wicked Good Guide to Yankee Vernacular. So, I will flip to a semi-random page. For anybody who doesn't know, I grew up in New Hampshire and listened to the stories of Down East Maine, which was brought to life by Marshall Dodds and Robert Bryan, who were two guys from Yale who in the 1950s heard tell that there was a group of Mainers who spoke a certain way, who had certain stories and ways of telling stories that were completely foreign to them, and they were like, this cannot possibly exist. So they spent a decent amount of time living up around what is known as Bar Harbor, or Bahaba, and tried to understand and try to get like the gist of how the stories worked, what the structure was. And I think they ended up doing like basically anthropological work on trying to understand how all of this worked in order to sort of save the art form of the Down East Maine storytelling style. So we are going on to, we're on D right now. Okay. Let's do this one. So, dressed like a deacon. Oh, I suppose some people may not exactly know what a deacon is. That's fine. No, okay. So deacons are like the members of the church who would mostly be helping out doing stuff around particular services and things like that. They would be generally the people who were like kind of making sure that the minister's job could be done. Not the people who were doing the service themselves, but people who were setting everything up, making sure everything was ready to go. So, dress like a deacon. All rigged out. All decked out, or all duded up. See deacon for a discussion of the derivation. The pious deacon has always been a low comedy personality in Maine affairs. And we'll connect that with deacon. Deacon, a verb, to arrange the apples on top of a box or a barrel so the customer presumes the same quality runs all the way to the bottom. Thus to put on a good front, perhaps a mild effort at cheating, but at least given an impression without backing it up. He deaconed his barn by painting the side towards the road. Perhaps an alleged sanctimoniousness of deacons is behind the term. Hey, Don. How we doing this evening? That's a very nice moo shark you have. Ooh, making baguettes. Nice. Let's see. Yeah, that could work. Yep, we're doing alright here. Kids got back to school. Not that we were off or anything, just we had a weekend. The base celebrated July 4th. Particularly with the baguettes you just made.
Now it's even easier to sell for free on eBay. Maybe I should sell that juice.
Yeah, I went to the grocery store this morning and walked out with a still warm loaf of sourdough. So, yeah, sort of. It's just that, like, they don't want to do it on the 4th. And like, this year, I think it's, what, on a Friday? Yeah. This year it's on a Friday, so they were like, So they did it on this last Saturday. And it may also have something to do with, like, I don't know if it's, like, getting close to the they would rather do it on the solstice for some reason, or like, I don't even know what their justification is, but if it was like, we don't want to do it on the 4th because then we make ourselves an obvious target, like, maybe, I don't know, but you're also broadcasting this. Like, everybody knows when the base is doing the 4th, so it's not a mystery. But I don't know. So we we went up there. There were food trucks. The scouts did the dunk tank. Little guys did their had coloring books to hand out as their propaganda pamphlet. I mean, recruitment pamphlets. So the Cubmaster's spouse, who is also a den leader and also just an amazing, like, leader and everything, leant down to my son and was like, okay, so do you want to, like, hang out at the table? And he's like, absolutely not. I want to go and say hi to my friends. And she was like, great, here's like 10 pamphlets, go hand them out to people who are with their, go hand them out to kids who are with their parents and ask them if they would like to have a coloring book. And he was like, got it. And he came back with none. So I'm presuming he didn't just throw them in the trash. He's actually, like, personable and stuff, so. Yeah, gotta get the scouts early. I mean, they convinced me when I was 5, 6 that I wanted to do tigers. And so my dad was like, all right, because he was in scouts when he was little, and he had done, like, maybe a little. No, I think he pretty much stopped once he hit 18. So I came home and I was like, I want to do this thing, and he was like, absolutely. And then from, like, then on, he was with the Boy Scouts for a while, and then ended up becoming Cubmaster of my pack for, like, the entire length of time that I and my brother were in it. Right? I mean, that's one reason to do it. But I ended up loving it. I never got Eagle, but I did a whole bunch of stuff, and I was the chapter chief of the Order of the Arrow. I was, like, you know, patrol leader and all this other stuff. We ended up having there were other people who were always senior patrol leaders, so like I never got in there for that one, but like fine, whatever. It didn't matter all that much. And like this was still in the 90s, so not a lot. The boys didn't do as much then as like they do now. The scouts now like have 100% control over almost everything that they do, and like the adults are just there to guide them and then help them like leverage things when they need it. So like, you know, oh, you work at this company, would you mind asking them for, you know, sponsorship for a particular thing? And especially in New Hampshire, like, I mean, this is true anywhere, but, you know, oh, we need like 10 tons of mulch. Not 10, but we need like a ton, literal 1 ton of mulch in order to cover this space. Would you, the person who works at the hardware store, be willing to, you know, go and ask your boss for a donation? And, you know, stuff like that. So you could kind of like ask adults to help, but they would never, ever, ever, at least nowadays, right? They would never be like, oh, here's an idea, let me do this for you. Nope. It's been working out really well. And I don't know if that's just like a you know, not New England thing. If New England was aberrant in the 90s, or if it was like everybody was doing that. But yeah, my scoutmaster was a retired submarine engineer. He was doing all sorts of stuff in nuclear power, and ended up working at Seabrook Station up in Seabrook, New Hampshire, which is the power station for like that entire area. He ended up getting us the, he ended up picking a weekend at some point, and we all got the nuclear power merit badge. It was like, yep, that's an easy one. Yep. So you go through like diagrams of nuclear power plants and like the basic idea of a nuclear reactor, and then we visited Seabrook Station, the power plant, because, you know, he works there, so it was easy enough. And then we did some other research. There was a little bit of a like small project or something like that you had to do to try to piece together how everything worked, and we ended up using Geiger counters to look at Fiestaware. Yeah, I mean, they've got a badge for pretty much everything. But yeah, the Fiestaware, that's it's painted with uranium paint. It is radioactive, but it's not like dangerous. You should not eat the paint if it chips off of it, but you can eat food that's been cooked on it. Nowadays, they tend to discourage the use of Fiestaware, but it's not like it's going to kill you. It's just, it's not going to like give you cancer or superpowers or anything. It's just moderately discouraged to eat off of it, because, you know, maybe not the best idea. Alright, we already said. Right, theta is going to be in quadrant 4 because it's coterminal to phi, which is 5 pi over 3. So 17 pi over 3 is within quadrant 4 as well. What you been up to today? 3. What are its trigonometric function values? So, yeah.
other apps. There's more to discover with Premium. Try 1 month free of charge.
I didn't know that it'd be so hard yet for me to relax. Don't know what makes me happy. Don't know what makes me sad. I sit around and ponder emotions.
Microcenter. What's a microcenter? Ooh, okay. Electronics store. Oh, is that brand name? Ah, nice. PC parts, yep. You drool over it, walk away, weeping. So let's see. With this particular one, again, this is a pi over 3, right? Theta prime is equal to pi over 3, and it's in the fourth quadrant. So that means that our x distance is going to be positive. It's also the short one on the 30, 60, 90 triangles. So that's going to give us, you can kind of figure out how you want to do this. You can either say that this is going to be a half, or you could say, well, this is going to be 1, and then the other side is just, you know, everything's going to be scaled up by a factor of 2. Again, nobody really cares. It's just kind of for your own edification. What are you doing? As long as you're not going to label something with a hypotenuse of 2 as the unit circle, you're fine. All right, so we get a 1 for our radius, and then our vertical value is going to be a negative root 3 on 2. Okay. Sine is opposite over hypotenuse. The hypotenuse is 1, so we're just going to ignore that. At this point, it's going to be the vertical value, which is a negative root 3 over 2. Cosine, same deal, horizontal value only. It's going to be a 1/2. Tangent value is, again, the slope of the terminal side, or you could do y over x. So this is going to be a negative root 3. This is a negative root 3 over 2 divided by a half. So it's going to just get rid of the 1/2 that's a part of negative root 3 over 2. Secant is going to be the reciprocal of our cosine function, so it's 2. Cosecant is going to be the reciprocal of our sine function, so that's going to be a negative 2 over root 3. Or, again, if you really feel like it, negative 2 root 3 on 3. Cotangent is going to be a negative 1 over root 3. Or, again, negative root 3 over 3. Just to be clear to everybody, I have said in the past, as a teacher, I would not care whether you rationalize the denominator or not. Showing me that, hey, look, this is the reciprocal of this other one, making sure the relationships are correct, and making sure that like you've got the right number is much more important to me than rationalization, which is much more dependent on you not having a calculator to figure out what the decimal value is. Right? You could just plug all this stuff into the calculator, get a decimal approximation to it, and do whatever other math you need to. The point is that you get the right value. The idea that everything has to be in this form, where we have a rational number on the bottom, or realistically an integer on the bottom, is basically saying that I can take something that is size 1, but how do I break it into the square root of 3 number parts? Right? There's not really a good way to do that. And for most of us, that would be a rather onerous calculation to attempt to do, because you need to put the square root of 3 on the outside of your division and try to, like, you know, do a decimal expansion to try to get it to work, or maybe find a different division algorithm that works nicely. It's gross. But on the other hand, if I know what the square root of 3 is as a decimal approximation, I can divide that by 3 super easy. So take, you know, I can also take a physical representation of the square root of 3, and I can cut it into thirds. Say, like, that's our final answer. Okay. So, if anyone has any questions, not that one. This is a problem for my experimental physics class. Using the Biot-Savart law, calculate the flux density. Nope. Unfortunately. I mean, I have not... Oh, you guys... Yeah, that's right. You did the, all sorts of physics. Generalize the formula you obtain to a regular n-gon with arbitrary integer n. Oh no. Finally, determine the flux density of the limit as n approaches infinity, so you get a circular loop. Alright. That at least makes sense, but... Woo! Right. Okay. So, next part. What is it asking? How do we... Oh, yeah. This is just getting us, like, all of the... This is getting us all of the identities and things like that. So, how do we do stuff like sine of negative theta? And how do we compare that to our originals? This is super easy. And it's going to be the same as, again, all of the rest of these that we've done. In that... if we have a positive theta here. And it doesn't matter where you put that, anywhere in the entire unit circle. Right, we also have a negative theta here. So if our original is located at xy, then where is the doppelganger? No, where is the negative angle going to be located at? Right, so we've gone to the right the same amount, but now instead of going up, we've gone down. Or likewise, if we went to the left, right, if this opened up this far into quadrant 2, our negative angle actually opens up into quadrant 3, and now we've gone again to the left the same amount. So our x value is just always going to be the same between the positive and negative angles. And the y values are always going to be opposite each other. So we always end up with negative y. These are in the opposite location. Again, if you change it to being, you know, angle in the third quadrant, you end up going here, then a negative angle of that is going to just go the other way and end up being up here. That's a terrible drawing, but that's not my problem, or that's my fault, but it's not, you know, going to change the math. This is still going to be the same x values and the opposite y values. So what does that mean for the sine function if we do sine of negative theta? Well, that gets us, again, the opposite y values. The sine is based on the y values, so we end up getting a negative sine value from the original angle theta. Okay, what about cosine? Cosine of negative theta. Well, the cosine is based only on the x value. The x value didn't change here, so it's the same as the original cosine of theta. What about tangent? The tangent of negative theta is based on the y values and the x values. Well, the x value didn't change, but the y did, so that's going to end up getting us the negative tangent of theta. And likewise, cotangent is going to be the same. Okay, and then if I'm honest, right, I probably should have gone this way.
Life throws challenges at all of us, but how do we cope? I'm John Roberts.
And said, well, okay, the sine is also related to the cosecant of negative theta, which is going to get us, again, the negative cosecant of the original theta. Cosecant is only based on the y values. And the cosine is much more closely related to the secant, because again, secant is based only on x values. So we end up getting just the secant of theta if we have the secant of negative theta. We don't have to worry about the negative that's in there. What does that mean for this? Well, we talked about this a long time ago. These four right here have a special property that when f of negative x shows up, we're allowed to state that this is the same as negative f of x. Hey, wait a minute. That sounds familiar, right? These are odd functions. And then our cosine and secant, likewise, we start with an f of negative x, and we just get f of x back. So these are even functions. Now later on in calculus, we can utilize a bunch of this symmetry in order to make things easier. And if anybody is like skeptical as to why these work that way or anything like that, you can always trade it out for the other statement. So the sine of negative theta was equal to, we said that this was going to be y over r. You know, the sine function is y over r. Sine of theta equals y over r. So again, our y values are opposite, so we get negative y over r. And then this makes negative parentheses y over r, right, which is the negative parentheses sine of theta. So we can do all that same stuff for all of these functions. Right, the cosine of negative theta is equal to x over r, which is just equal to the cosine of theta. Right, that doesn't change. Yes, we're still here. Right, so repeat all of those properties if you want to prove to yourself that all of these even and odd symmetries exist for any particular function. For the trig functions, you can use these particular definitions. But for literally any functions, you can do something similar to this. Break it down, define what it means, list out its definitions where relevant, and then try and relate the negated input to the definition of the original function in some way, shape, or form. If it's straight negative, awesome. If it's just 100% the same, awesome. If it's neither of those, then it doesn't have the even-odd symmetry. It's going to have something else going on. So parabolas, for example, if they're off-center from the xy axis, right? If you've got a parabola that's down here somewhere and your axis is over here, this is neither even nor odd. You're not going to get any symmetry except along its individualized line of symmetry. But the function itself will not have symmetry in the same way that the sine and cosine function here does. Hey Syntax, how's it going? Doing more trig tonight. You have the three things that just always go together. Okay, so then what do we do for stuff like the sine of alpha plus beta? Right? This is going to be not equal to, very important, the sine of alpha plus the sine of beta. All right, because this is a feature of linear operators. So the sine function is not a linear operator. And if you ever looked at a sine function, you could probably tell, yeah, okay, that's not a linear operator. Right? This is a very curvy thing. You're not going to end up with a linear function anywhere on it. And again, the sum of angles is not going to get you the same thing as the sums of the sines of two angles. So it's very easy to also disprove, right? If you want the sine of, I mean, hell, let's just go 290s, right? If you want to get the sum of two 90-degree angles, yeah, okay, when they're very small, it's close, but that doesn't, no. Right? Alpha and beta equal to pi over 2. Then what we end up here is, this would be the sine of pi over 2 plus pi over 2, which would be the sine of pi, which is 0. If you remember, this is the vertical value. Pi is exactly 180 degrees off from 0, and it's along the x-axis. So what's its vertical distance from the x-axis? It's 0. However, if we said take the sine of pi over 2 and add it to the sine of pi over 2, right? This is an obvious counterexample. This is 1 plus 1, which is equal to 2, which is not equal to this. It's the idea of tangent spaces.
With YouTube Music Premium, listen to your favorite songs ad-free. Download music and podcasts to listen offline or on the go. Enjoy thousands of customized playlists and radio stations. And jam to music when your phone's off or while using other apps. There's more to discover with YouTube Music Premium.
Well, in that case, syntax, right? If you've got the cosine of two angles which are very close to 0, then you've got the cosine of each of their angles, which you're trying to sum up, and then in that case you get 1 plus 1 equals 1. So, right? Very nearly 1 plus very nearly 1 equals 1, or very nearly 1. So that doesn't work either, right? It's going to be very nearly 2. When you get two large things together, when you're talking about large in terms of sines and cosines. So this does not work in terms of sines and cosines. It'd be nice, but no linear operators here. So instead, what we do is we start from a geometric perspective. It's not really all that surprising. I do it all the time on this channel. So we say that we're going to look at this from, roughly speaking, something like this. Right, this is not a very good not a very good setup. Ugh. Oh, shoot. Delete. I tapped instead of just moving. Okay. And we take a second one out here. Right? Now these are not particular angles. I'm just trying to pick something that's going to work here. So what we've got is, let's call this one beta and this one alpha. Okay, now it is theoretically possible to make, you know, alpha plus beta, but that involves taking beta and like sticking it on the end out here. That's kind of a pain in the rear to have to move stuff. So when you have overlapping values like this, alpha and beta, which overlap each other, it's actually a lot easier to work with the stuff that is non-overlapping. So in this case, this is alpha minus beta. Right, and I want to, well, I want to copy it, but it's not going to be 100% useful. Okay, so we want to deal with the coordinates that deal with alpha and beta such that we can talk about the angle alpha minus beta. All right, where are these locations? Well, this is x comma y, but as we remember from before, as long as r is equal to 1, and we can let that happen on, you know, an arbitrary circle, we'll just say, sure, r equals 1, we can scale it up or down from r equals 1 to whatever r we want later on. Right, without loss of generality. We're going to say that our x value is going to be the cosine of beta in this particular location. Again, our x values were going to be the cosine length for that particular angle on the unit circle. The vertical distance is then going to be sine of beta. And likewise, if we go over to the other one, this is going to be the same for alpha. So cosine of alpha, comma, sine of alpha. Now these are two arbitrary angles that we picked. Could have been in any quadrant, could have been in any arrangement whatsoever. So we don't have any like particular... We don't have any particular angles that we're working with or anything like that. There's no way to simplify this super easy. So what we're going to do is we're going to say, all right, look, we need to talk about something that's not going to change if we move things around and make it a little bit easier. This angle that we have, alpha minus beta, is not in standard position. So it'd be much nicer to talk about if it were in standard position. So in order to get it in standard position, all we have to do is take this whole thing and rotate it a bit until it falls over. Can't rotate, can I? No. What? Okay, there we go. I think it was there if I do one of them. Nope, never mind. That's edit line. Okay, so basically what I'm going to do is I'm going to take this line and I'm going to rotate it until it reaches the x-axis. We put it in standard position, right, where our x-axis is 0. Then we have to do the same thing, so move the same angle here that we did for the initial side. We also do it to the terminal side. So here we say, wait, is that it? Yeah, it is. We're going to rotate that much. Awesome. Which then, again, this is going to rotate this to there. Now moving the beta out there is just like an indicator as to what we had formerly. It's not really, I'm not doing anything here. All right, and this means that we now have these two locations that our angle is going to hit here and here rather than here and here, right? It's changed what locations exactly it is on the circle. However, it has not changed the angle between those two lines. So here we have, this is 1, 0. And this point up here, its x value is the cosine of the angle that goes from 0 up to this line, which is alpha minus beta. That's pretty awesome. Comma. the sine of alpha minus beta. Okay, now that we've got this, these are two different things that have exactly the same measurements between them. How do we know this? Well, if we want to really get technical, we could have said, hey, wait a minute, this can form a triangle that goes between those points. How do we know they're the same? Well, first of all radii are the same. So there's a side and a side. And the angle between them is alpha minus beta. Right? On both of them, it's alpha minus beta. All we did was tip it. So now we've got a side, an angle, and a side. Or two sides and an angle between it. Side, angle, side. So we know that these two triangles have to be congruent to one another. They have to be identical by side, angle, side congruence. And that therefore means that the distance between them is going to be the same on both of these triangles. Like, yeah, sure, the angles are all the same, but like, yeah, that's fine. We don't need to worry about that. It's not all that interesting. The distances, though, are going to be the same. And now those distances are represented in two different ways. The distance on the left side is going to be given by
some things belong on the big screen.
Right? We get a right triangle that goes between these things. So now we need the distance squared is equal to the difference between our x values. So cosine alpha minus cosine beta, parentheses squared, plus parentheses sine alpha minus sine beta, the difference in the y values. Right? The distance traveled in the vertical direction, the distance traveled in the horizontal direction. You square those distances, add them together, we have a right triangle here. And d squared is going to be the square of the hypotenuse. On the right, same deal. D squared is equal to, oh, well, look at that. That means that these things must be equal to each other as well. So over here, we get parentheses cosine of alpha minus beta minus 1 parentheses squared plus sine of alpha minus beta minus 0 parentheses squared. On the right, we can expand all this out. This is going to get us the cosine squared of alpha minus beta minus twice the cosine of alpha minus beta plus 1. Plus sine squared of alpha minus beta. Okay, and then the rest of the other two terms are multiplied by 0. So we don't have any linear signs, we don't have any constants on the sine part. And then over on the left, we have cosine squared alpha minus 2 cosine alpha cosine beta plus cosine squared beta plus sine squared alpha minus 2 sine alpha sine beta plus sine squared beta. Alright, and there's some really interesting and cool stuff that goes on because of that. right now what we see is that there is a cosine squared alpha and a sine squared alpha, which are being added together. Don't do that. Which are being added together. And a cosine squared beta and a sine squared beta, which are being added together. Let's maybe do it totally. Charlie Brown it up. Right, and on the other side, I mean, we could just do a different color, but that's not the point. On the other side, we've got a cosine squared of alpha minus beta and a sine squared of alpha minus beta. Hey, guess what? Right, okay, we're good. So on the left, this is now cosine squared alpha plus sine squared alpha is a 1, and a cosine squared beta plus a sine squared beta is a 1. So adding them up, we now have 2. Okay, and then we get a minus 2 cosine alpha cosine beta minus sine alpha sine beta is equal to, on the other side, we now have a green, we now have a green 1 and then a salmony colored 1 minus 2 cosine of alpha minus beta. Well, that means that this 2 here and these 2 here are going to subtract out. That also, we owe that one a 2 here. All right, we also can divide everything in the entire equation by -2. So we get a cosine alpha times cosine beta plus sine alpha times sine beta yes, right. I'm good. Is equal to a cosine of alpha minus beta. All right, so now we get what happens when you have a cosine of alpha minus beta. It's all that. All right, and then if we want cosine of alpha plus beta,
Discover new music with a swipe on the YouTube Music app.
then we can make that cosine of alpha minus negative beta. So we get a sine alpha times a sine of negative beta here, plus a cosine alpha, cosine alpha times cosine of negative beta. Remember how we just discussed evens and odds, like even and odd functions? Well, this means that cosine alpha times cosine of negative beta is an even function, so it's just going to be cosine beta. It's the same thing. Plus sine alpha times, the sine function is an odd function, so sine of negative beta is going to be negative sine of the original beta, which now is cosine alpha times cosine beta minus sine alpha times sine beta, which is the cosine of alpha plus beta. And again, if we want to do this with all, I don't have time for it because we're going to hit an ad break, but if we look at this in terms of what angle we have again, right? This is the cosine of alpha plus beta. So, let me think. Oops. Right, if this is our theta, and this is our pi 1 over 2 minus theta. Alright, we're going to hit ads, so I'll stop here for 3 minutes. See you in just a little bit. Thanks, everybody.
Now it's even easier to sell for free on eBay. I was thinking, maybe I should sell that juicer we've used a grand total of once. Or the shirt I've been saying I'll wear for the last 2 years, but never have. Or that tiger cushion the dog barks at every time he's in the lounge. Oh, is that it again? No, Bertie!
With new AI listing features and simple delivery, it's now even easier to sell for free on eBay. Download the app now. eBay, things people love. T's and C's apply. Excludes vehicles.
Hi again. Anybody who hasn't been here in quite a while, or caught me on a night when I've actually done stuff with sticks, this is Escrima, which is a Filipino martial art that is based on the use of machetes. So it's also applicable to Chinese broadsword, but generally speaking, it is a very much sword-based art. I'm actually looking forward to seeing how it applies to my karate, which, granted, right, it's not going to apply 100% directly, but it's got some decent, there are some decent similarities. So, let's see. I forget what there's a three move thing. So we come across, oh, that's right, go like that, and then we're back over here. So it's a 45-degree strike down, like you normally do in pretty much everything we do, but then it comes back up around while this one comes across, and then strikes down again at a 45-degree angle. So it also allows you to end up switching sides. It's a little bit like this, but at the same time, it allows you to strike literally twice with one side. Blah. Anyway, we'll also do my Tai Chi form, because that's due in a couple of days. Not that we're actually testing or anything like that, but usually spend my Wednesdays with my instructor Wednesday afternoon, and then we get some time on Thursday night to do stick work with a different group. Okay, so something like that. So from here, I gotta be more careful about this. So from here, we lean back onto the back leg. We're locking our stance in so that we're not able to really be pushed back any further. We're letting it come at us, essentially. We pluck. Step in. I did this far too quickly before. And then what we're doing from here, we're coming back, pluck, allow the momentum of the person to carry through, and then we're allowing that to either strike the person or aim further back here. And this is going to be you kind of let your hand flop, and it's a bit like the Escrima doing the outside. When we use the sticks and do an outside hit like this, we stop with our heel of our palm on the forearm, and it allows the stick to kind of whip. So we're doing the same thing essentially with the palm as well. So we bring it from here and like let it fly, and you kind of notice how it, like, no matter how I stop it, no matter how much I try to keep this as long as it's not like rigid, it kind of just flops around a little bit. And that extra little slap there adds a huge amount of power. All right. Again, if anybody has any questions, let me know. Otherwise, I might be able to snipe some questions from other people's streams. There's not really anything to snipe because everybody's too awesome. This week in Tai Chi, I was there with this other lady who is a Shotokan student and has been doing Shotokan for basically as long as I've been doing karate, I think. And we both got to a certain point of doing some sort of technique, and our instructor just starts laughing, and he's like, "You both did the exact same thing, and I can tell exactly what schools you all are from. It is very obviously karate." We're like, yeah. Okay, so if we look at this and we say that this is our, let's not use x, let's use cosine theta. This is our sine of theta. Yep, okay. I remember how to do this. So what we're doing is we're going to say that the cosine of no. What we want is the sine of alpha plus beta. Right? It's going to be really useful to now have the sine of alpha plus beta, but we don't have it. So the problem at the moment is that we need to say that the sine of theta is going to be equal to the cosine of pi over 2 minus theta. Okay, so that's going to say that the sine of alpha plus beta is going to be equal to the cosine of pi over 2 minus alpha minus beta. And we can choose which one that's going to associate with. So let's commute and make this cosine of negative alpha plus pi over 2 minus beta. And we will associate those two together. Which is cosine of, since we're doing addition, this is going to be a huge pain in the ass, but it's fine. Since this is addition, this is going to be the cosine of the one we just did. Negative alpha times the cosine of pi over 2 minus beta. Oh, wow. That's nice. Okay. Minus the sine of negative alpha times the sine of pi over 2 minus beta. Yeah, I just realized what that's doing. Okay. This is going to be the cosine of negative alpha, which is also the cosine of alpha. Multiplied by. The cosine of pi over 2 minus beta is the same as the sine of beta. Right? So over here, there's nothing wrong. You just don't want to keep running. Oh. No, okay, that's a commercial. Right? This is going to be the sine of pi over 2 minus theta, which is equal to the cosine of theta, the thing that's opposite it. This vertical one is the cosine of pi over 2 minus theta, which is the same as the sine of theta, which is opposite it there. Again, it makes a rectangle, so those opposite sides have to be equal to each other. So here, this is now going to be minus the sine of negative alpha is going to be negative sine of alpha times sine of pi over 2 minus beta is the sine of beta. Okay, so this is the sine of alpha plus beta, which is going to be equal to, let's flip them around and get the sine of alpha first. Oh. Oh, no. That's a cosine. Right, the sine of pi over 2 minus beta is the cosine of beta. There we go. So sine alpha times cosine beta plus cosine alpha times sine beta is the sine of alpha plus beta. And then if we want the sine of alpha minus beta, this is going to be the sine of alpha minus negative beta, which is equal to sine of alpha la la la. I can't hear Elvis. Da 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 da. You guys, seriously, you cannot play that music. Sine of alpha times the cosine of beta, cosine of negative beta, plus cosine of alpha times sine of negative beta. Okay, which is equal to sine alpha times cosine is even. Hey, Zach. Minus the cosine alpha times, again, the reason that this works this way is that this is the negative sine of positive beta. So we could just kick that negative out front. Make it this cosine of alpha times the sine of beta, which is the sine of alpha minus beta. I've proven it a different way before, but I like this better, just because it works off of basic principles. It works off of the other trig that we learned before, simple identities, and making sure that we making sure we do our algebra correctly. It worked without you typing. Man, that's like a lurk bomb. I want to get it to do the same thing as pens. Like I want it to pop up on your first message so that it actually, like, you know, is consensual. At least somewhat. So that way you could just lurk if you feel like it. And you could be guilt-free.
Time ain't always go time. Set the positive, set time out, and set reality checks. Stay safe, players.
Right. So this is the cosine of. Now we have a cosine of alpha plus beta and a cosine of alpha minus beta. So we could do this as the cosine of alpha plus beta, because all the stuff is the same except the sign that's between them. So as long as we put it in the correct order, cosine alpha, cosine beta. Now here's the thing, right? The signs that we ended up getting in between the stuff was opposite the signs we had between our angles. So here, if we put a plus minus on alpha plus minus beta, then we're going to have to put a cosine alpha cosine beta minus plus sine alpha times sine beta. Go that way. Right, and then we get the other two here. And this is the sine of alpha plus minus beta is equal to, this was the sine of alpha times cosine of beta. And here our signs were always the same between the two groups. Cosine alpha sine beta. Yeah, I mean, where do you think Ramanujan got it? Stated without proof. In all seriousness, no. Right. There's where we get the sum difference formulas. Now, if we want the double angle formulas, it's super easy. Why? Let alpha and beta be the same thing. Have I seen the geometric version? Probably haven't. Oh, come on, yes, I'm human. Yes, I have seen those. Yep. Oh, why do you do that? The rhyme that's just after those diagrams, yeah, it's gonna kill me. Don't do that to people. I do also like that one. Yup. The one with 39 upvotes. Or should I say 40? Mm-hmm. Use the complex representation. Oh my goodness. Use the series definitions. Oh, why would you do that? No math, no tricks. Nix the tricks, right? Okay. So with alpha minus alpha, you could verify that the identity is correct by getting cosine of 0 equals 1. On the other side, it's the two cosines, which when you take their product, you get the cosine squared of alpha, and alpha 0, so cosine squared of 0 is going to be 1 squared, which is just 1. The sines end up getting you sine of 0, which are sine squared of 0, which is 0. No, that's not how that works. Sorry. Dot dot dot. That's a cosine. Okay, there we go. Cosine squared of alpha plus sine squared of alpha equals 1. So the right-hand side is going to be 1 from cosine squared plus sine squared. Oi. Been a while since I've done it out. Da 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 da. And then we get the cosine of 2 alpha, which is going to be equal to then the cosine squared of alpha, but now it's a, since this was a plus, this is now a minus. And that's a sine squared alpha. Right, I guess I should do that one extra step out, because, you know, I confuse myself, so it's conceivable everybody else is confused too. It's all good. Okay. Cosine of 2 alpha is going to be the difference between the cosine squared of alpha and the sine squared of alpha. And then when we go to the sine part, this is going to be, again, sine of alpha plus or minus alpha. Right, this is going to be the sine of 0 is equal to, this was the sine alpha, cosine alpha. Since it was a subtraction between the angles on the sine of 0 side, it's going to be a subtraction between the cosine of alpha times the sine of alpha and the sine of alpha times the cosine of alpha. So that is the same as each other, so it's equal to 0, which makes sense because, again, sine of 0 is 0. And then we get the sine of 2 alpha, which is now going to be equal to the sine of alpha times cosine of alpha. But now it's a plus between them. Cosine of alpha times the sine of alpha. And those are the same back to front. Right, so we get 2 sine of alpha cosine of alpha. Okay, now this one's great, but that's not it, right? We could, if we really wanted to. You got a required reading about that for your math elementary education class. Ah, interesting. Rules expire. Yeah, that's fair. So if I don't particularly like sines, I can say, hey, look, that's a sine squared of alpha. I can change this to become a, you can argue which way you want to make it go, but sine squared of alpha is equal to 1 minus cosine squared of alpha. Or negative sine squared of alpha is equal to negative 1 plus cosine squared of alpha. You could also just plug it in and multiply, it's all good. But here we get a cosine squared of alpha, not infinity, right, minus 1 plus cosine squared of alpha. So that is now 2 cosine squareds of alpha minus 1. It's also possible. But when you think about it, as George Carlin said, that also means that the cosine squared of alpha can be rewritten as 1 minus sine squared of alpha. Or, no, I don't need to do that. Never mind. 1 minus sine squared of alpha. So that means that I now have 1 minus sine squared of alpha minus sine squared of alpha, which is equal to all right, 1 minus 2 sine squareds of alpha. So I now have 3 different representations of cosine of 2 alpha depending on which squared version I want. Do I want one that's all cosines? Do I want one that's all sines? Or do I not care and just give me the difference between the cosine squared and sine squared? Can do any of them. In terms of sine of 2 alpha, you really only can do the one, right? 2 sine alpha cosine alpha. You could play around with it and see what happens, but yeah. I don't believe I have... Oh, it does. Lets me through. I don't have membership, but that one is not paywalled, so. Interesting symmetry in which way, I suppose. I would say it's arguably somewhat reminiscent to, like, binomial square, but yeah. There's always 2 trigonometric functions somewhere, yeah. Whether it's both in the first mixed or both in the second. That's fair. Okay. Let's see. Yeah, okay, so then the double angle formulas also lend themselves directly to doing the half angle formulas, which, like, gets somewhat annoying here, because it's just like, oh, look, there's like 20,000 different trig identities you can make. But the basic idea here is that if we take the cosine of 2 alpha is equal to 2 cosine squared alpha minus 1, what we can now do is relate the single alpha in terms of the double angle instead. So these are all called, again, double angle. Identities. These next ones are called the half angle identities, but realistically, like, I don't remember them most of the time just offhand. I start from the double angle identities and work backwards. It takes me an extra, what, like 5 seconds? So if you're studying for an exam, sure, do that. You know, have these in your back pocket as something that you remember. But I would remember them from using them, not from, or like from deriving them, not from just memorizing. We keep talking about it on a number of our channels, but every time you memorize something, it's just kind of like, well, this information is essentially arbitrary. Like, I could exchange it incorrectly in my head, and I wouldn't know the difference. Except if I, like, try to use it, it doesn't work. Oh no, what do I do? If you know where it comes from, then you can at least back up to, you know, your last stable configuration in your brain. And then be like, okay, I know that this works. Now, let's try to derive the other one. So here, this allows us to say that, like, cosine of 2 alpha plus 1 is equal to 2 cosine squared alpha.
Hey, did I prove this time off?
Can't chill.
Okay, and then here we can divide by 2 on both sides. So we get the cosine squared of alpha is equal to 1 plus cosine of 2 alpha all over 2. This is also known as the power reduction formula. For cosine. If you want to... no, that's usually a good one. Just uses it from here. Alright, then we say that this is cosine of alpha is equal to, this is the square root of, and this is an absolute value technically. 1 plus cosine of 2 alpha all over 2. Realistically, this is also written as a literal half angle. So the cosine of theta over 2. Right, if we let 2 alpha be equal to theta, then alpha becomes theta over 2. sine. We'll do plus minus, because that's also how it's written somewhere else. Generally speaking, these are going to be positive, but it's not always the case. So just keep an eye out. 1 plus cosine of theta all over 2. Alright, so one of these representations will do something for you. Okay, and then we go to the other one, which was the cosine of 2 alpha is equal to 1 minus 2 sine squared of alpha, which, again, moves stuff around a little bit. This is going to be sine squared of alpha is equal to 1 minus cosine of 2 alpha, all divided by 2. And wouldn't you know it, there's your other power reduction formula. Right, get a sine squared to become, in this case, cosine of 2 alpha. But power has been reduced from 2 to 1. And then again, take the square root of both sides, you get the sine of alpha is equal to the square root of, I'm just using absolute value again, cosine of 2 alpha all over 2. Right, and then this means that the sine of theta over 2 is going to be equal to plus or minus square root of 1 minus cosine theta all over 2. And if your original alpha is between, or I guess your original theta in this case, is between 0 and 2 pi, then the sign here will always come back non-negative. Might be 0, but it'll come back non-negative. So that's fun. And again, one of these 3 representations will do it. As long as you remember one of them and where it all comes from, you're fine. Alright, now we finally actually get to a question in the book, because they wanted to run through all that trig first. Right, so then the question from this entire section is find the tangent of pi over 12. Now, I have my favorite strategy. Which is to get this as a representation of 12ths. And then simplify to something a little bit easier. In this case, 1 pi over 12, we're going to have to add, subtract, realistically, 2 numbers, 2 multiples of pi over 12, which when subtracted will give us 1 pi on 12, and when in their unsimplified form can be individually simplified. So here, 4 over 12 minus 3 over 12 is going to get us the 1/12 that we need, and it's multiples of pi. 4 pi over 12 is pi over 3, and 3 pi over 12 is pi over 4. Alright, then my personal way to do this is to say, well, tangent is the sine of that same angle. So pi over 3 minus pi over 4. Divided by the cosine of that same angle. Pi over 3 minus pi over 4. You could do it whichever way you want. There's some people who just memorize the tangent formulas. And again, if you memorize the tangent formulas for an exam, sure, cool. You did it. Good job. But if you forget why that exists, or you want to double check it, or anything like that, again, it's a really good idea to remember where all of this comes from. So the sine of a difference of angles is going to be the sine of the first one times the cosine of the second. Our functions are unalike, and the sign between them is alike. So it is going to be the same as the negative up top. And go the opposite way. We need all four combinations represented. So this has to be the cosine of pi over 3 multiplied by the sine of pi over 4. Right? Every combination represented, and like and unlike functions and signs between are a staple of this whole section. So whether you remember that or not is irrelevant. It's just something that's interesting to me. Right, with the cosine, we actually have like functions, but unlike signs between them. So here we go with a cosine of pi over 3 times the, like functions, cosine of pi over 4, unlike signs, plus sine of pi over 3, sine of pi over 4. Equals sine of pi over 3. So if you don't remember what it is, again, pi on 4 looks like this. We got 1 root 2, or 1 over root 2, 1 over root 2, 1, depending on how you want to look at this. This also means that you do have to watch out for your scale factor of r, and pi over 3. It's going to be a 1 root 3 and 2. Sine of pi over 3 is root 3 over 2. Cosine of pi over 4 is root 2 over 2. Minus cosine of pi over 3 is 1 over 2. Times sine of pi over 4 is root 2 over 2. These are all in the first quadrant, so they're all going to be positive. Divided by cosine of pi over 3 is 1/2 times cosine of pi over 4 is root 2 over 2, plus sine of pi over 3 is root 3 over 2 times sine of pi over 4 is root 2 over 2. Which is square root of 6 over 4 minus root 2 over 4, all divided by root 2 over 4 plus root 6 over 4. Multiply both top and bottom by 4. Get rid of all of those individual fractions, and so now we get root 6 minus root 2 over, if we just look at the bottom and rearrange, they're both positive, so that's fine, root 6 plus root 2. If you insist, or if the exam insists, then we need to multiply both top and bottom by the irrational conjugate. And what we have is the square root of 6 minus the square root of 2 needs to be multiplied both top and bottom. Down bottom, this is going to get us 6 minus 2. That one's super easy, right? We end up getting, this is a plus b times a minus b. So we get a squared minus b squared. And since these are square roots, squareds are nice and easy. Up top, we get root 6 by root 6 is again 6. We also get at the end a positive root 2 times root 2, because we have two negatives multiplied together. It gets us at plus 2. However, we get a negative twice the product of the two of them. So root 6 times root 2, which is simplifiable. We'll do that in a second. Okay, this is going to be equal to 8 on top and 4 down bottom. And then we get a minus. The root 6 by root 2 is going to be root 12, which has a 4 inside of it. So the 4 is going to get square rooted, come out as a 2, and then we get root 3. So minus, this is the 2 that was already here, times the 2 that comes out from the square root. So we get 4 on the outside. Square roots of 3. Okay, and then this is simplifiable. So the tangent of pi over 12, last bit, is equal to, divide everything by 4. We get a 2 minus root 3 over just 4. Nope, not 2. That's a 12. So tangent of pi over 12 is going to be 2 minus root 3. And again, if we could stop way back here, right, that would have been a correct answer if we don't mind irrational denominators. All right. Let's just check the next page real quick. See if we got. Oh yeah. Oh, that's just pretty right there. Okay, one last one. If sine of theta equals 1 over 3, find the secant of 2 theta. You jerks. Okay. Do not find this formula. No. Okay. So instead, what we ought to do. Instead, what we ought to do is say if we have the sine of theta is 1/3. This is telling us that, right, we have an opposite side, which is going to be 1, and a hypotenuse of 3. So then what is the horizontal side? Well, this is going to say that, again, r squared is equal to x squared plus y squared. We don't know what x squared is, so x squared is equal to, this is going to be 9 minus 1 is 8. So the absolute value of x is going to be 2 root 2. So this also means that now the cosine of theta is going to be equal to 2 root 2. But that's an absolute value because we don't actually know what quadrant this is in. That's not true. I'm sorry, that's over 3. A. Oh, wait, hang on. Oh. Yeah, we're pretty much done. No, wait. 2 theta. Okay, never mind. Okay. So the horizontal side is going to be 2 root 2. But we don't know if that's actually positive or negative, and we'll just deal with that in a minute. Rather than doing the secant of 2 theta, what we can do is make the secant of 2 theta instead 1 over the cosine of 2 theta. I know how to deal with cosine of 2 theta. That's easy enough. Furthermore, what numbers do we have? We have the sine of theta. So put that in there. Right? We've got a cosine of 2 theta formula that uses only sines. Do that one. So cosine of 2 theta is equal to 1 minus 2 sine squared of theta. This is 1 minus 2 parentheses 1/3 squared. Which is equal to 1 over 1 minus, this is 2 times 1/3 squared is 1/9, so that's 2/9, which is going to be 1 over 7/9, which is 9 over 7. Bingo. And just to make sure, 9/7. Yep, cool. So always, if you can, go back to the information that you were given and try to use that as many times as possible. Try not to use something like cosine of theta, because if you were wrong anywhere in copying it, or if you were wrong anywhere in deriving it, you could have completely lost out on this entire question. But even if we ignored the x distance or cosine of theta entirely, right, if we had ignored this 2 root 2 entirely, that still allows us to find what the secant of 2 theta is. So remember that this is 1 over cosine of 2 theta, and it's done. All right. Any last minute questions? I do mean last minute. Okay, so Dr. Gold is on, so we will. He's been up for almost 2 hours though. Usually he stops. Oh, how are we doing? They're celebrating just finishing a problem. But, I think we're going to go see Paleontologizing, who is Dr. Denny Anduza. He is currently on a dinosaur dig, and on day 24 of this particular dig, he is digging up Cretaceous critters at Turtle Hill. I don't know exactly where that is, but so we'll head on over there and say hi. I think next time we'll end maybe a little bit earlier and go see Dr. Gold. So anyway, thanks everybody for coming. We'll be back on Wednesday for more mathy type stuff. Friday for gamey type stuff. I think we're doing Against the Storm. And then at any point other than that, we might be doing something else. I got a game gifted to me from my brother called The Swapper, which I think it seems like one of those you can only play this once type games. And I've got a few others, including Nine Souls, that I would like to play on stream, so we'll figure out exactly when we want to do that. So, thanks everybody for coming. My name is Obi-Wan Pez, this is N Simplex Pachinko. We'll see you next time.